Hey everybody, today we're going to be talking about VSEPR theory. So we're going to be talking about the geometric structure or the molecular structure of molecules in 3D. And this VSEPR thing is an acronym that stands for valence, shell, electron, pair, repulsion. Okay, so the main idea behind valence, shell, electron, pair, repulsion is that electron pairs push away from each other. Okay, so to kind of give you an idea of what I'm talking about, suppose this yellow ball here represents an atom, and we've got some electron pairs, and these could be lone pairs like the dots in your model, or these could be bonding pairs like a single bond or a double bond or a triple bond. And these things, because electrons are negative, negative repels negative, are going to push away from each other and try to get as far away from each other as they can while still surrounding some atom that's in the middle of a molecule. So, if I had, like this little thumbtack here, if it represents an electron pair, if I had another electron pair on this atom and there were only two things pushing away from each other, that other pair would need to go to the complete opposite side of the atom because they would try to get as far away from each other as they possibly could. If I added a third pair, then, maybe those three pairs push away from each other, something like this, and try to evenly space themselves around a flat circle. If I had a fourth pair, this starts to get a little bit more complicated. It actually forms something called a tetrahedral, where, you've got, like, if I can get it right, three of the pairs are kind of pointing downwards a little bit, and one pair is pointing upwards. And if I were to flip this over, you can still see one's pointing upward, and then the other three are kind of slightly downwards, like a tripod kind of scenario. So that's four pairs pushing away from each other. Now, basically, you need to tell how many pairs are pushing away from each other and involve the atoms to try to predict what the 3D shape of a molecule is going to look like. So in order to do that, we're going to use something we've already done, and that is to create a Lewis structure. So the first step is to make a Lewis structure of the molecule. Okay? And then after we've created the Lewis structure, we want to be looking for electrons that are surrounding the middle atom, and those can come in a couple of different forms. Sometimes they are, you can count the lone pairs on the middle atom. And here's what I mean by that. Okay, if you've got an atom that's in the middle of some other atoms and you see a pair of dots, this is a lone pair. Okay, that's one pair. And you can have more than one pair. Maybe you had another pair down here. It kind of depends on the structure of the molecule. And then you also want to count the bonded atoms. Okay, so suppose I had a molecule that looks, I don't know, something like this, where the middle atom is double bonded to one, single bonded to another, and I've got a lone pair in the middle here. The count here would be one lone pair, because I only had one lone pair. And if there's lone pairs out here on these other atoms, those lone pairs don't matter. Okay, so you're only counting the lone pairs that are on the middle atom, and you're also counting the bonded atoms to the middle. You're not counting the middle atom, we're just counting what's around the middle atom. And so if we were, had a structure that looked like this, the bonded atoms to the middle would be 2. Okay, don't count this double bond as 2 separate things. That double bond would still just be one bonded atom connected to the middle. So, you know, in effect here, this would have 3 different areas of electrons that are repelling each other, kind of like I was doing in that foam ball a minute ago. Okay? Once you know both of those things, then you should have enough information to be able to predict the shape. Or, you know, if you want to get fancy, predict the molecular geometry. Okay. Now, I've got some reference for you here, and this reference is kind of the same as what you're going to find on the back of your green sheet. So if you look on the back of your green sheet, there's a little table, and it's going to have some information similar to what you're seeing here. It's going to have, you know, the number of atoms connected to the middle, the number of lone pairs connected to the middle, and then the electron pair arrangement. This is really the shape that we're talking about. This is the molecular geometry of the molecule. And if you want to, you know a little bit about the geometry itself, if you were talking about the angle between pairs, you know, if I had a couple of electrons here and I measured the angle between the pairs, then that column there would tell you the angle depending on how many things you've got repelling each other. And this last column here, I'm not really going to talk about too much right now, but we'll get back to this. I don't really like this in your reference because it's not on your green sheet, and we're going to do that a slightly different way. Okay. All right. So you can see here that, you know, there are, you know, different combinations of the number of atoms connected to the middle and the number of lone pairs. So an example of kind of this first scenario here might be, you know, suppose you had a CO2 molecule and you had a carbon that was double bonded to a couple of oxygens, you know, something like this. In a Lewis dot structure. This would be a scenario where you had 2 bonded atoms and no lone pairs. 2 atoms are connected to the middle, and we have no dots on the middle. The effect of this is that you only have 2 things trying to get away from each other, which is going to produce a molecule that's straight across, a linear molecule. And in 3 dimensions, that might look something like this. Okay, and you can see all 3 atoms are in a line. Now, if you were to have a molecule like, let's say H2S, this molecule would have 8 total valence electrons, which would require you to put a couple of lone pairs on that middle atom in the structure. So it's actually more this scenario than the one scenario here. And you'd have 2 atoms connected to the middle and 2 lone pairs. Now total, that's 4 things trying to get away from each other. So total, that's more like this scenario where we had all 4 things trying to get away from each other, evenly spaced around the molecule. But you've only got 2 of those electrons actually connected to other atoms. And when we're describing the shape of the molecule, we don't really describe the lone pair's shape. We describe the shape that the atoms are making. And so the effect is that you're going to get a molecule that looks something like this. Now, the lone pairs are still taking up space and repelling the electrons that are in the bonds. So there's electrons in these bonds, but those lone pairs are taking up space and forcing the other atoms closer together, and so you end up with this bent shape. This molecule happens to be bent at an angle of about 109.5 degrees. Okay? All right, say you had an SO3 molecule. Well, if you build the Lewis dot structure for SO3, it would require you to put a double bond to one of the 3 oxygens because you just wouldn't have enough electrons to get the sulfur stable otherwise. So the molecule here would look something like this. And if you started looking around that middle atom in the structure, you'd have 3 atoms connected. Remember, that double bond still counts as just 1 atom connected to the middle. So 3 atoms connected to the middle and no lone pairs. Now, so you got 3 things trying to get away from each other. This is going to basically make a molecule that's a flat triangle. That's what planar means. Planar means flat. Okay? So trigonal, 3-sided, and flat. That molecule might look something like this. Okay? A flat molecule. There you go. Okay, trigonal planar. Now, if you had, say, a NH3 molecule, like say N attached to 3 H's and a lone pair in the middle. This is nitrogen trihydride or ammonia. You know, here we've got basically one addition to what we had up here, and that is the lone pair on the middle atom in the structure. And so we're back to a total of 4 total things trying to get away from each other, just like we had up here with this H2S molecule where we had 2 and 2 atoms and 2 lone pairs. Here we've got 3 atoms and 1 lone pair, but it still totals to 4. And for that reason, the distance that those electron pairs are getting away from each other is still 109.5 degrees as an angle. And so, you know, you end up in a scenario this time where you've got 4 electron regions. That maybe there's a lone pair up here, but the other 3 connections to atoms that are bonding pairs are going to be oriented in a way where you've got this little 3-sided pyramid. Okay, so trigonal pyramid, pointy on top. So the difference between the trigonal planar and the trigonal pyramid is that the pyramid, you know, is pointy on top. Okay. If you have 4 bonding pairs and no electron pairs on the middle that are lone pairs, maybe we're talking about an atom that looks something like this, CH4. Okay. This is methane gas. All right, this molecule here is a tetrahedral. You actually have all 4 things connected to other atoms, and that's going to end up in a configuration that looks something like this. You always have one pointing up and then the tripod of the other 3 atoms kind of pointing down. It doesn't matter if you flip it over, it's still the same, and all 3 would be, all of the atoms would be 109.5 degrees apart from each other if you were to measure that angle. Okay. Now, there are some other exotic shapes that honors people might need to know. I'll get into those in another video. Okay. Let's talk briefly about polarity just for a second. All right, so normally, you know, I teach that the polarity of the molecule is based on the shape, and I just give people this polar, non-polar stuff. But I had a student last year that kind of pointed out something to me that was a pattern, and that was that pretty much if you take a look at which of the shapes are polar versus which of the shapes are non-polar, you can see it's polar if there are dots on the middle, and it doesn't matter if there's 1 pair or 2 pairs. The other polar shape also has dots on the middle, and all of the non-polar shapes do not have dots on the middle. And this has to do with the fact, really the shape of the molecule, but in general, lone pairs tend to make molecules that are not symmetrical in 3 dimensions. That means they're not going to evenly balance out in terms of the way electrons are being pulled. Okay, so the real explanation behind this, you know, just to kind of give you a couple of examples here. Imagine that this was a CO2 molecule. And if you were looking, you know, at the dipole moments of the individual bonds here, oxygen would pull electrons that way from the carbon, and this oxygen would pull electrons this way from the carbon. And those 2 pulls are equal and opposite. So the electrons are not really getting pulled more to one direction or the other in the overall molecule. Now this is still a polar bond between one of the carbons and the oxygen. So this is a polar bond, but the entire molecule is nonpolar if you look at it as a whole, because the 2 polar bonds cancel out with each other in terms of the way that they're pulling electrons. Now, if you know, contrast that to, say, the H2S molecule here, you know, if this were an S in the middle and these were 2 hydrogen atoms on the ends here, then those hydrogen atoms would not be able to pull electrons as well as the sulfur that's in the middle. So, you know, the sulfur is pulling electrons better than the hydrogens. Now, if that was straight across, then you would end up in the same scenario before, and this would be nonpolar. But the effect here, because the shape is a little bit different, is that electrons get pulled up and in, at least the way this molecule is oriented here, and up and in, and those 2 directions sum to an overall pull that goes up. And so, you know, if we're looking at this bent molecule here, the top of the molecule would be partially negative, whereas the hydrogens at the bottom of the molecule would be partially positive. Okay, now that tends to happen anytime you have lone pairs on the middle atom in a structure. It's going to be a polar molecule because the shape just lends itself to scenarios where you're not going to have pull